So it's a great pleasure to be here giving these doctoral courses. I'm Demetrio Filho. I'm professor at the University of Brasilia, and currently I'm fellow in residence for the period 25-26. I have already a long history, let's say, of relationship with this center, and that's why I'm really happy to be here giving this course. I have been fellow in residence for all the periods, 19, 20, then 21, 22. Now it's the third time, and I'm really glad this time we could find, with the help of Amen, a spot that we could take to share with the PhD students and postdocs and whoever is interested a little bit of my knowledge that I have been gathering for these past years of research. I decided to present a course on a subject that is very kind of me. I really love this subject, which is the scientific writing. I was thinking about why. To pull it up. You see? Mm-hmm. I was thinking about why this is so dear to me, this subject, and I believe because when I was a master's student, late 90s, write the paper was boss job. No one could do it, so it was almost like prohibited for students to write the papers. So you deliver the data to the boss. Maybe if you are really good in English at the time, which was not the case, you could write a draft, but most of the time, boss just put the draft aside and he will do the job. So it was almost like an honor to the boss to write the paper. And of course, it was a different time. English was not popular. Courses of English was very expensive. And we did not have for example, the command of the language that, for example, you probably have nowadays English command. No? So when I spent 7 years in the States, I came back, and when I arrived at university, I started to teach scientific writing, just giving the basics to the students. I had a very nice textbook of a professor in Brazil who wrote a text more like towards the mindset of us Brazilians in the Latin language, as we will see, is very complicated, very complex. We like to write a lot, lots of details, and this is almost in the opposite direction of scientific writing. Scientific writing has to be concise, precise. So we have to exercise a lot, especially as Brazilians, with Portuguese as a Latin language. So I took this book, I started these courses, and I have been doing it since then for the past 16 years. In 2023, there was a big change in scientific writing. Students of mine, undergraduate students, graduate students, that had the difficulty to write few pages, now would come with documents. And guess what happened in 2023? ChatGPT, right? So ChatGPT completely changed the picture, and we know everybody's using it, but everybody don't say much about it. And big problem is no one knows exactly what are the dangers. Not even ChatGPT knows. You know, the people who build. Yesterday, I got a message in the internet saying, "Oh, they discovered that ChatGPT is feeding up with text created by Grok." So The other competitor AI is generating text. It's an AI generated text, and ChatGPT is learning with that. So what will happen? No one knows. So we are in the beginning of a big change, and the quantity, the amount of papers, if you look, all the curves, you extrapolate, you can see that there was a jump in 2024. So it's obvious that people are much faster, producing more text, etc., etc., etc. So in this, I had that in mind to prepare these 6 classes. And the idea is we will have the first 4 classes are basically what I used to do in the courses in Brazil. Oops. So I will start with the definition of scientific research. It's sometimes people say, oh, but I know what scientific research is, but I think it's interesting to us to really name the points exactly, because sometimes when we are writing our paper, we need to keep that in mind. What are the basic aspects of scientific research, right? Sometimes nowadays, I feel like the scientific research is being charged with the applications. Every university, every grant proposal, they want us to come up with an application. So we are kind of mixing up what is really the deal of scientific life, thinking that to be good science, it has to be an application. And this is really not the case, right? And sometimes at LPPI, I know it's very common that you have companies involved in the financing of research, and this is we have to be very careful, because the goals of the company are different than our goals as scientists. As scientists, we want to contribute to science, we want to publish papers. As companies, they want patents, they want to make money. So these two things, they can live together. It's important to learn how to put them together, but we have to be very clear of the boundaries. So we will not step into the other boundary and then we end up not having a product, not having a paper. Everything is possible. So I will talk a bit about scientific research, and then we'll start with the structure of an article. This is traditional course of scientific writing. We will dissect a paper, starting from the title, what is a good title, an abstract, etc., introduction, give some suggestions of questions and how you can go building up your text to write your article. Then I will give some hints on how effectively do the scientific writing. And here enters also, for example, some suggestions from a Google designer that I found her book very interesting. Little changes that you can make in your figures that may change quite a bit the understanding of a figure, of a graph. Sometimes it's difficult to extract information from a graph, and sometimes only doing some coloring and changing that I will show in the 3rd class, you can improve quite a bit your figure. Then we will go to a very important point, which is the bibliographic research, right? Sometimes with the AI, is much easier nowadays. In the past, it was extremely complex to do bibliographic research. I remember first time I was in the library in the States. I don't believe we had in Brazil these books, the scientific indexes. They look like the Bible of Abraham, huge book, and you open book and you find the keywords, and then in that book you will find the papers that you try to search. Nowadays, you see Google, give a keyword, you have thousands of papers. Easy, no? But at that time was not easy. Even papers, my boss, nowadays when I come to France, I have my bags full with books. In the past, my boss would go back full with papers. He'd come to the States, he'd come to Europe to get papers because it was difficult. It was expensive to have the subscriptions of all the journals. So every time he would go abroad, he would profit to go to the library, take photocopies of papers, and bring them back to Brazil. Nowadays, we have a gigantic quantity of papers, and now it's even a problem because how can we read all of them? In my dissertation, in my thesis, I have a pile of papers, which was the papers I had everything marked up. I knew all the details in each paper, and that was it. It was a pile. Nowadays, you find papers, for example, with 1,000 citations. How can one read 1,000 papers to write one on? Just fine. It's difficult. No? So we have to give some strategies for you, first of all, to separate what is good from bad. And second of all, once you have your much larger pile of papers, how can you start to process the information there and save it? Because 3 years, 4 years after, you have to write your thesis. And can you imagine that you remember everything that you took notes if you do not take notes properly, etc.? Impossible. So we'll give some tips on that. And then I will prepare 2 classes where we will talk a little bit about AI. So first, the idea of ethics in scientific research and AI use. All the universities in the world right now, they are on a process of trying to help the students, professors to identify what is okay, what's not okay in AI use. There are some universities, they have already some directives. We see, for example, in journals now, there are some journals, they ask if you use AI and you have to tell yes or no. And if you use, you have to say where did you use, how did you use, etc. So from the journal perspective, I think it's like a disclaimer part because it's really hard to detect for sure the use of AI. So they put a disclaimer because in the future, if we develop a tool that can precisely, and I believe this will happen, precisely identify the use of AI, the journal say, okay, I asked, he said no, so now it's his problem. My colleagues and I don't know anyone who said, I used, and what happened? I don't know. Because that's the question, right? You say, oh, I used to deduce that. What happened in the process of peer review? They rejected, they said, no, if you use, okay, it's your problem. I don't want to touch it. I don't know. So far, most of what I have been reading is either they say he didn't use or they changed to journal, to another journal. That's not that. So it's a complicated situation. And then I will talk about the AI risks, which is really the most important. What is the risk that you are putting yourself into when you are feeding the AI with some text of yours, for example? You're writing a paper. For example, one of the uses that people are not blaming, they do not say it's a misuse or a misconduct, is to use AI for translation. Right? We had, before ChatGPT, we had a very famous software called Grammarly. Grammarly would go a step further than some simple dictionary or corrector, right? It will help you to rewrite the sentences and correct some, not only the words, but the grammar faults, etc. And no one ever complained about grammar, right? Everybody should use. So the translation is some acceptable use. But what is the problem when you give your text to the AI? Imagine you discovered something really interesting and you just give your text in your own language to AI to translate. AI translates it for you, and what it does with your information, no one knows. No one knows. The training of an AI algorithm is the business secret of the company. So no one knows. No one knows the answer to this question. But we have some hints. And one of the hints, for example, the New York Times processed OpenAI, and they proved that for certain questions, the output of ChatGPT was text from New York Times, ipsis litteris. So they could prove they used our journal and they didn't pay us. So they sued OpenAI. I'm not following the process, but I believe they will have to pay because you cannot use any source that's not public. New York Times, you have to pay to have access to it and make money with it without paying the source, right? So no one knows. And when you sign the contract with OpenAI, there is this terrible word that is may. Your information may be used. May, there is a huge hole there that can go through this hole, right? So it's possible that you end up giving up your idea to someone else. That's true. So if you, here we have the dates. If you plan to be here, these two, I think, is the most important of the course. It will happen right after the winter break, and March 11, March 18. So please save on these dates to come here or to watch online. So we start with the definition of scientific research, class number 1. I will have 4 topics. The idea is 4 topics, we give a break, and then we keep going for more 4 topics. The idea is if you want to interact and make questions, English, French, okay, no problem. And during the break, I will start see if there is anyone in the audience online that wants to make a question, or you can put in the chat, and Karin will help me read the questions and we can answer in the break, and then we can keep going. Okay, so what is scientific research? So we like to define things in the beginning, so then we can build up the concept. I took just one definition that I liked, I think is interesting. It says scientific research is a systematic and transparent process aimed at generating new knowledge or understanding based on testable evidence and critical reasoning. Every word here was very carefully used, and at the end of the class today, I will tell a story that it was an horror case in the United States when I was there. One physics professor said it was the most terrifying moments of physics in the past 50 years. That was 20 years ago, so nothing more terrifying happened in these 20 years. So like a very terrifying story in the past 75 years. I was kind of in the middle of the area, so I know well what happened. And I brought this story as a bonus at the end of this class. And you will see that every aspect in that story is against what scientific research has to be. A systematic and transparent. So one of the points that was crucial, there was no transparency. When you have papers and we cannot reproduce the results, or the results are kind of shady, or the equipments are not very well described, there's always an issue. So scientific research has to be transparent. And that's why there is no way to conciliate scientific research with patents. Because at the end, when you patent something, you want to protect, so you don't want to, before, of course, when you put the patent, in the patents, everything is described. But if you publish a paper and you have the intention of patenting, this will not work. Because in the paper, you have to open up everything. You have to give the recipe of the cake, how all the details, how to prepare the cake, and someone has to be able to do the exact same cake, right? So the idea is to generate new knowledge or understanding based on testable evidence and critical reasoning. So we have to put our minds to think, design the models, etc. So systematic, the keyword systematic means it follows a very logical structure and a methodology. So one of the most important parts of the paper is the methodology. We have to clearly state what we have done, make sure all the details are well described. Transparency, so all methods and assumptions that are, they should be explicitly stated. Evidence-based, what means? Science is based on data, ground data, observations, or formal models. Sometimes there's no data. There was this story of the shortest chapter in science, which is a chapter of the string theory, which is chapter 1. There is no evidence data for this theory. Chapter 2. There are theories like that. No evidence, no data. It's just a model. Okay, but you have to prepare the model and maybe you will be able to test it, right? And the reproducibility. This is another part. Remember this word because, again, when I tell the crazy history of physics at the end, there was no reproducibility. Reproducibility not for the person that was publishing the papers. He said everything was reproducible. Of the community. The community couldn't reproduce the guy's results. And that was scary. And that's against scientific, right, research. So here we have a chart that I like most that says the scientific research process. So it's a process that takes several steps. And here it starts with the question, the scientific question. Sometimes I like to talk to PhD students and graduate students in general, and I ask, what's your scientific question? It's important that you have clearly in mind because the scientific question drives all the research process because it starts with the question, then you design a methodology, then you gather evidence. This word we hear a lot in the police, right? In the police environment. They gathered evidence. There was a T-shirt there, etc. Evidence here is more than data, as we will see. Evidence is data that has been processed with the method. Then you will start to do the interpretation of this evidence using your methodology. And then sometimes, and most of the times, especially in the experimental physics or chemistry, we can take this interpretation back and generate new experiments to make sure our interpretation is correct. So we can test our methodology, we can test our evidence. And at the end, the scientific paper comes to crown all the process, which is communication. So at the end, everything is done. You come up with your paper that will be refereed by the community to crown all the process, which is the scientific research process. Okay, goals of scientific research. When I ask you this question, the answer can be very quite a bit. You know? If you ask a researcher, he can say, "Oh, I like it. It's really fun." The goal is to have fun. I like to go to the lab to do my synthesis, etc., etc. If you ask someone in the street, a layman, person may say, "Oh, it's the scientific research," especially the politicians, and they like to say, "Oh, it's very important to our country to generate revenues and jobs, and so that the humanity will go to a better place, etc." A very nice discourse. But the goals of scientific research is pretty much work on these 4 items. Number 1, describe what the phenomena that you are trying to observe, right? Identifying patterns, structures, regularities, observations, data. You gather data in your laboratory, you want to describe what's going on. Once you describe, this description goes beyond just tell what's going on, but is to identify, and this is a very important group of keys, underlying mechanism. What is the underlying mechanism? Is really what is moving those engines, right, and producing the results. So the Richard Feynman, he had a definition of scientific research that he was on a beach, and gods were playing chess, and all he could see was to observe the pieces moving. That's all what as scientists we can do, observe. So as we observe gods playing chess, we start to figure out some rules. Those are the underlying mechanisms. Sometimes, most of the time, we do not have all the mechanisms. So we have the most important mechanisms, right? And this is important to try to build a model that will be able to, in the third part, make the predictions. That third part is really what makes the scientists happy. I cannot imagine how much Einstein was happy when he was in Brazil. Einstein was in Brazil one time, and he was there in Fortaleza to look at eclipse, because a tiny little difference in the time of the light that will cross, you arrive on Earth, will be a prediction that his theory was right. So he traveled all the way from Europe to Brazil, went all the way in the northeast of Brazil, in the middle of nowhere, with the astronomers that were making the predictions. And at the end, boom, he was right. The light will follow a curved path and will take a little more time. Relativity was right. So this is the goal. Gather data, make models to try to predict. Once you have these 3 in hands, then there are some areas where you can make applications. So once you know what is the background, the underlying mechanisms, most of the time, not all of them, the most important, Then you can make predictions, you test your predictions, your model is good. Then you can say, okay, now I master this device, this system, this mechanism. Now I will try to do some application. But here I make it very clear. Applications is a consequence of the knowledge, not its definition. So it's really not the case that we try to build or to search in scientific research a definition of applications. Use applications to drive scientific research. It has to be the other way around. Scientific research will be done, and at the end, we may have applications we log. And I say that because nowadays we see so many products that came out of scientific research that in the beginning, the application was way far. No one could ever see that experiment in the laboratory. Someone, I remember when I was a student, there was a professor, he was building a big equipment that in the end, after 30 years, became a tomograph. Like that we go inside and make all these marvelous images, right? But in the beginning, the idea was not that. The idea was to study atoms, study the magnetism in atoms, etc. If if we look at that and say, where's the application? Oh no, I'm only studying hydrogen and water. Oh, okay, so forget about it. We don't want it. And then you kill right in the origin some marvelous applications like we have today. So that's why we cannot use applications as the drive of scientific writing, of scientific research. We will discuss about the scientific, the papers, the sections of the papers in another class. But right now I want to give you just this one-to-one, more or less, correlation between the definitions of scientific research, and this is what motivates this class today, this first class, and the sections of a paper. So there is a one-to-one. In the description, you will make it in the methods and also in the results. The explanation, discussion, prediction, usually you give in the conclusions some of the possibilities of extending your article, your research. So now let's go to the most important part of this class in this first part, which is the research question and the hypothesis. They are linked together. So what is the research question? So a research question is a clear, focused, and answerable question or questions that guides the direction of scientific investigation. So you have to have a very clear question in your mind to really move in the scientific research, in your research project. I got two sentences here, one of Einstein that says, if I had an hour to solve a problem, I would spend 55 minutes thinking about the problem, and I added here, thinking about what is the question first, and 5 minutes thinking about solutions. So this is, of course, is Einstein. So maybe we would spend 1 year thinking about the questions and 2 years thinking about the solution. This is us who are mortals, no? Einstein would spend only 55. But this is the idea to give you the importance of defining a scientific question. And there's another sentence that I don't know who say that, but is known among the scientists, that says a well-formulated scientific question is already half of the solution. So once you formulate very well your question, you already have a very good start of your research. So Before starting gathering data, making experiments, trying to this, try that, discuss with your advisor and make sure you have clearly stated a group of questions that you want to answer. Will these questions stand all the way to the end of your thesis? Probably not. Why? Because in the process, remember scientific research is a process, you may find new questions that are much more important than the first ones, and that you will feel more pleasure to answer the new questions than rather than the old ones. So it's not set in stone, as we used to say. It's not set in stone, but never start moving without your questions. So they have been clearly defined and specific, grounded in existing knowledge or observation. So you will not end up in the States, they have this expression, goose chase. So you not start running in any direction, making some fancy questions that no one can answer. It has to be grounded on existing knowledge. And the idea of existing knowledge is exactly the beauty of publications, because you add up this existing knowledge and you extract from the literature questions, and those questions can be important for you to answer. Answerable with scientific methods, and of course, relevant to the field of study. Relevance is always important. I share with you, for example, one question that is burning in my mind right now. So what is the idea? We have at LPPI a table of polymers with lots of properties, monomers and small molecules, and we have experimental data gathered by people from LPPI for all these years, and we have theoretical simulations that we can create more data. Example, absorption spectrum. All this data is relevant to characterize the so-called calorimetric coordinates of a compound. So these colorimetric coordinates are very important for LEDs, for light emitting diodes, because this will give the color of that LED. So what is the question? Is it possible to train an artificial intelligence algorithm capable of estimating the colorimetric coordinates of a new compound only using its geometric structure and theoretical calculated data? So this is the question I have now. So what is the idea? Imagine you have an idea, a new molecule. You know it takes a lot of time to synthesize this molecule, right? And usually chemists, they are very colorful, they are very creative. They never have one idea. They have dozens of molecules that they have in mind. Very hard to synthesize. So can we calculate the properties of this molecule, spending only energy, not hours synthesizing the molecule, and using an algorithm, an artificial intelligent algorithm that has the data of all the molecules that have been synthesized, have been calculated, have been characterized experimentally. Using all these two things together, can the artificial intelligence do a good guess of what would be the calorimetric coordinates for this new compound that is not synthesized yet? That's the question. Okay, so, and what we are doing? Trying to work with the people from computer science and etc. to see if this is really possible. There are situations right now, for example, with artificial intelligence, that we cannot tell the answer without testing. We have to take the method and test. And sometimes someone developed a method for a completely different application. And we just change a little bit the parameters. We put this into the program, and it gives the answer. And this is just evolving as fast as we are. So sometimes it's difficult to predict if the answer will be yes or no, but this is the question.
Like,
yes, please.
Aside these questions, like, how can we evaluate that these questions is answerable or not?
Very good question. I just mentioned that sometimes we have to try, right? That's the beauty. Sometimes in the PhD, especially in the PhD program, sometimes we start with questions that they have dead ends. You go there, oh no, here, have to come back, and we have to start with another question, right? This is the difference. For example, when I'm thinking about a master project and a PhD project, the master project, I need to see the end. I need to propose something that I see the beginning, the way the student has to go, and the end. I have to see the end already before it starts. But the PhD, the idea of the PhD is to create new things. So in principle, the end of the story is not written yet, because it's to create new things, right? How can you guarantee that that question that your advisor gave to you in the beginning will be answerable? No guarantee, zero guarantee. What we do? Well, we ask more than one question. That's a good idea. Why? Because if you cannot answer one, maybe you can be more lucky with another, right? And then, so I always say, I always have a backup plan for a PhD program. I always have some backup plan. So you start with this question, with this set of questions, system, etc. But there's also another project that you write in parallel with way more clear. It's already more clear that this will work. So if this thing, which is in science, we can think about high risk, high gain, right? If you risk something and if it works, well, you can be almost a Nobel Prize. But it's high risk, high risk. So there is also a risk that it doesn't work. So what happens? You end up without a PhD? No. You have to have a backup plan, right? The second set of questions, more easy to answer, that will come up with a paper, that will come up with a result that will satisfy the community, that will guarantee your PhD. Very good question.
But like for the ground, you said that it should ground with existing knowledge. Like maybe if we with some experience and the results go shown very high, like it's not follow the trends of our publications. So how do you think that like this can be a breakthrough result, or it can be some errors of the experience or like this? Like why we should follow the ground existing knowledge. Like if the result have some new result and it can be the new model, how can we evaluate that?
Very, very good question. The point is, sometimes when we see exciting results, we really believe we are in the right path for a Nobel Prize. But the ground in the best results tell us to be a bit more careful and to really observe what is going on. I have a story for you that I like very much, which that came from a Nobel Prize, Alan Heger. So Alan Heger, he said he was in his Christmas celebration with his group. So it was the last day in the laboratory. Everybody in the lab eating, drinking, make party, etc. And there was someone measured. Someone was making measurements. And the measurement was the conductivity of some polymers. At the time was really a must to find conducting polymers, conducting plastics. No? That's why he got his Nobel Prize for the evaluating conducting polymers. And the student was making these measurements as a function of temperature. He was reducing the temperature and looking at the conductivity. And the conductivity was going down or going up, normally, boring, grounded in what people have been doing. The idea there was just to test new polymers. All of a sudden, the conductivity jumped to infinity. Oh, conductivity jumps? What means? What means? I discovered an organic superconductor. Okay, let's repeat. We repeat it again, measuring, conducting, going, as usual. All of a sudden, it jumped. At a certain temperature, it jumped. I found the superconductor. And we run to the lab, to the other office. Please come, let's go to the superconductor. All excited, everybody went there. Oh no, there is a Nobel Prize tomorrow, etc. So the party was 10 times more fun because someone in the lab discovered the organic superconductor, the first organic superconductor. Well, but the winter break ended. Everybody came to the lab. Boss came with the students. Let's do this measurement again, my son, because we always have to have our feet well grounded on earth before starting thinking about Nobel Prize. And we go very slowly, jump. Let's open the system. Let's see what's going on. So when they opened the sample, it was everything closed in a cryostat, right? Measuring temperature as a function of temperature. The sample had holes on it. So the measurement was using tips that touched the sample to make the contacts. But as the temperature was going down, dilatation, etc., the tips were puncturing the sample. And what was going on there? Short circuit. That was it. So the conductivity that was high compared to a metal was transitioning quickly to the conductivity of a metal. It was much lower. So at the end, when he seen the plot, a jump to infinity. Okay. So that is the point, the danger of when you have results that are off the grounded in the literature. But you're right. You found something very new that can be an advancement. This happens all the time, also, right? And sometimes this can give Nobel Prizes quickly as well. We see the case of graphene, for example, something that gave a quite quick Nobel Prize for something that was more or less simple. So my suggestion to you is always repeat the experiment. Make sure there's no puncturing the sample. There's no someone that opened the door at that time in the middle of the measurement, changing the parameters, and then temperature went up, etc. And approach with lots of care. And the point of interest also is the community is always, the peer review process is always, as you see the second part, is always a buffer exactly for this kind of problem that may happen, right? So imagine there was an example here in France, not so long ago, that they made measurements of neutrino speeds, and they saw speeds higher than the speed of light. And so, oh, Einstein was wrong. There is something that moves faster than the speed of light. And hushed, etc., and everybody found group in France found the speed faster than light. This may put in check the relativity theory, etc. And the community gathered, okay, let's analyze what's going on. What was going on? Statistical measurements, statistical errors. Right? They were not doing very well the measurements and taking into account the errors, the statistic bars, etc. Okay, no relativity say C is the highest speed still. The Einstein is still correct. So that's the community. The community, if sometimes someone goes publish some results without lots of scrutiny, the peer review process is there to already hold a bit. Okay, do this experiment again. Try to do this, try to do that. Make sure this is not a mistake, this is not a flaw of your system, etc. Everything passed, your paper is out, people will start to repeat the experiment. Did they repeat? Yes. Oof. You're safe. You're right. You discovered something. You were the first one to publish it. You have your place in history of science. Not that they will help you to find what may be the causes of the result. Sound reasonable? If you have any other question like that, I'll be glad to answer, because they are very good. Okay, so the evidence is exactly what you will be gathering to discover your phenomena. So it's observable, measurable, and computable information. So the evidence can be empirical. That's what we like most, because this is nature, right? The experiments. But there's also the theoretical and computational evidence that is possible. Nowadays, very common. We can use computer to simulate lots of systems, and these are also very important evidence. A key point among all of them is evidence is always testable and verifiable. So we have to be able to test and verify evidence. Without testing and verifying, then it becomes other things, not science. Okay? So the idea is all the experimental data that you have, someone with the same equipment has to be able to verify it. Now, is it always the case? Is it always the case that someone will be able to verify your experiment? Do you think it's possible? For example, you have your problem that you are working on your PhD, you publish a paper. Do you think someone anywhere in the world can redo everything? Most of the cases, it is, right? If the person, if you're not using some equipment that is fantastic, no? Just regular equipment, synthesis, you bought the compounds from chemistry, whatever, you did the synthesis, prepare the films, everything is written on a paper, someone has to be able to reproduce it, right? But this is not always the case. I give you an example. This guy, finally, once he discovered superconductivity because he was able to liquefy helium. At that time, he was the only one who had an helium liquefier. No one else could have the measurements he was doing because he was the only one that could reach below liquid nitrogen temperature. So, but what happens? Science catch up, right? So at a certain point, someone patented the helium liquefier, someone started to sell the hidden liquefier, then everybody could reach 4K, and the results of superconductivity could be reproduced. But in that little window of time, he was publishing papers just like, oh, take iron, with below temperature, published. Okay, now let's try copper, superconductivity temperature here, published. Keep going. This is what the Americans say, the low-hanging fruits. So sometimes you find imagine an apple tree no one has found before. So where you go? You go up to the top to take the tree? No, you go take the low-hanging fruit, the easy one, right? Take all of them, and then the others will have to work out more to take the other fruits. So data is not evidence until properly analyzed. Once you analyze, then data turns into evidence. Evidence may lead to different conclusions as it must be interpreted using assumptions, models, and statistical or logical reasoning. Common problems processing evidence, for example, over-interpreting limited data. This was one of the examples of the neutrino high-speed light problem. So there was limited data, interpretation was not really done on statistics, and they come up with results sooner than what would be. So ignoring the uncertainties and error bars, and of course, treating models as facts. No? So this idea of string theory, for example, string theory is a model. There is no experiment attesting it's right or wrong. And sometimes when you treat models as facts, I think who likes a lot is Hollywood, because in the movies of parallel universes and things like that, they are really cool, right? But it's a model, right? We don't have evidence it exists. We don't have evidence that indeed there is another universe that this office is full of people. For example, we don't. Okay, so we have to be careful with when you have models and we treat models as facts. So the evidence consists of data that has been interpreted and evaluated in relation to some specific hypotheses, models, assumptions, and reasoning. This point, I have a story that's interesting to remember. Is the story of Tycho Brahe. So Tycho Brahe, he was an astronomer in Denmark. He loved to look at the sky. He was just looking at the sky all the time and making measurements, precise measurements, very well organized, with the data, high precision, etc. He couldn't make sense of these numbers. He couldn't make sense of what was going on, but he was annotating everything. And luckily for science, all these tables of Tycho Brahe ended up in the lab of who? Kepler. Kepler looked at this people. Oh, there is something here. And he had his ideas, he had his models, and all that data, and said, nature is speaking to me. He is speaking to me. And he announced 3 laws of Kepler. With a relationship, for example, in the third law, r cubed divided by t squared equal constant. And he figured out that relationship with the numbers of Tycho Brahe. Can you imagine a relationship like that? It could be anything. It could be r to the power of 1 divided by t to the power of 1, 2, 3, 2, any possible combination. And he had no calculator at that time to make all these combinations. So Tycho Brahe had data. Kepler put together his model with evidence, transformed data into evidence, He had his assumptions, his reasoning created 3 laws. But what about the underlying mechanisms? Remember this word, underlying mechanisms. Kepler didn't know about. It took 50 years, a little more, for Newton to say, look, the underlying mechanism is universal law of gravity. Masses will attract each other with the force inversely proportional to the square root of the distance. So this is all about science. Data, models, then you have predictions. And with the law of Newton, they start to predict a bunch of things. One of the most beautiful predictions I learned not long ago was the discovery of Neptune. So Neptune, the planet, they discovered it making calculations. And the guy who did the calculations tell an astronomer, look, they at that day, etc., put your telescope in that direction. You see a planet there. No one had seen Neptune yet. So all calculations, all models using universal law of gravitation. The guys, that day, he was with the telescope there, when he saw, there was a planet there, Neptune. This is really nice, man. The prediction of science. So the evidence is the bridge between observation and knowledge. Data becomes evidence when analyzed and interpreted. Evidence is used to support, weaken, or refute scientific claims. Without evidence, claims remains only opinions and hypotheses. So data is really important that you gather your data very well organized, keep like tissue drive. Remember of tissue drive? He had nothing but pen and paper. Everything, all the dates, etc. Organize your evidence, because this evidence can support, weaken, or even refute the scientific claims, right? And sometimes to keep this raw data, one of the problems in this history, I will tell you at the end of today's class, was a misconduct. So that the person was really doing bad. He was really trying to hide the evidence, right? Because he was trying to fool everybody. But the idea is, if he had not this intention, he would give up his evidence. Other people would be able to run tests on his data and see that something was going on. But he was hiding it. But he had bad intentions in his mind. So that is the problem. Okay, so in this second part,
aside, like, when I try to find some papers for my bibliography, my supervisor said that, like, if you want, when you find papers that have very proof, the results of that out the trends, just forget this. And this question is that in my mind that, like, why I should forget this result, like it is, maybe I'm missing some really interesting phenomenons result, or it's just the result they create, or some error with this result. So how can I clarify that?
Great question. I have a nice story about that as well, which actually was the origin of a nature journal of Nature Protocols. So you know there is a journal that's called Nature Protocols. Why Nature Protocols came up? So in the beginning, for example, in the organic devices, you could make organic devices like by the hundreds, LEDs, for example, right? You made a matrix of 100 LEDs, 100 by 100, 10 to the power of 4. And you make these matrix, and in the past, when people would publish the results, what they would do, they would test all the devices. They will take the best one, and they will say, oh, but this was usual numbers that we got in our lab. And it was not true. It was the best of the group. So people started to really be mad, especially those who follow the protocol that says you have to make a matrix, lots of devices, average number. You don't draw the bad number. You don't draw out. You keep them. You make the average. You make the standard deviation. These numbers are important. It's not the maximum that really matters. You need to make the average. So after being sick of having papers who say maximum speed, maximum mobility, etc., then they realized the best way was to impose the good judgment, impose a protocol. You want to publish now data on LAD, you have to do this. You have to create a fixed number of devices, you have to average, you have to show the standard deviation, you have to do this, you have to do that. Oh, so and now you can even create a protocol for a new kind of device, and you can publish as a nature paper, as a nature protocol. So when your advisor tells you that, I understand what he's saying, because sometimes indeed you have numbers that they are not statistically well treated. Because when you treat them statistically correctly, pictures may change a little bit, right? And the results that are so astonishing, maybe they will not be so astonishing at all. So when you see these astonishing numbers, sometimes indeed it's something that's below the hood, that you have to take it and review. But of course, you really need to check who is writing the paper, in which journal, right? Because sometimes, as I said, the peer review process, it's very strong to do that, to stop people just publishing results without scrutiny, without really doing the right analysis, the statistical analysis, etc. So in this, if you take, for example, a paper showing special results in Journal of American Chemical Society, I would dump this paper. I would keep it. Right? This is not common for a paper that goes in JATS without being punched a lot, right? By the so I believe this scrutiny there is very strong. But is it possible that it may be just not as good as it is? It is, and you see why? Because there's always this idea of the authority, right? We still have this in the peer review process. So in the peer review process, the authors are known. The reviewer, we don't know, but the authors are known. And sometimes it comes from a very important group, in a very important laboratory. There is this argument of authority. Oh, this guy cannot be publishing garbage. No? I don't know why the result seems a bit wrong, but it comes from the laboratory of blah blah blah. So you still have to be, just cautious to write. Right? But keeping that in mind, don't actually expect, very nice results. Don't trash them, keep them, but select good journals, sources, laboratories that that are doing good science. That's the idea. Did I answer your question? Thank you. So reproducibility. So the idea is that independent researchers, they can and they should obtain consistent results using the same methods and data, right? So this is a point that I want to stress, that this is the foundation criteria of scientific validity, of scientific research. It's a foundation criteria. It's not an optional ideal. So ideally, people would verify, no, this is foundation. We have to verify um, the data. Reproducibility, of having someone reproducing your results, enable error detection that we were discussing, right? People just being sloppy on the measurements, etc. It verifies the claims. So say, oh, I got a mobility that's higher than everyone else. So if people reproduce it, it verifies this claim. And it helps to the cumulative scientific progress. So results that cannot be reproduced cannot become scientific knowledge. So if you can't reproduce it, cannot be science. If it only happens once, sorry, you have to make it happen again, because it has to be reproducible, right, to be science. So the scientific methods, they must be described to sufficiently detail, allowing independent replication. So what is the idea? You create your device, you generate data. On your paper, you have to describe every step with sufficiently precision so anyone else can reproduce that. Vague or incomplete methods undermine reproducibility. And when you see that, for example, in the paper, there's always the feeling of why this person is hiding that, right? Is there any reason for hiding the details? And as I will tell at the end of the story, the community has learned in a very bad lesson what is behind the papers where they do not describe the methods very in very detail, right? So the describing methods requires clear definitions, explicit assumptions, precise experimental and computational steps. So if a method cannot be written clearly, it cannot be tested or reproduced. So while thinking about your methodology, always think about a person that will take the paper and will follow your steps to reproduce it. And this is good to make it very clear. Remember that in the paper, sometimes you don't need to put everything. There's always the supporting information that can go lots of information more than what is in the paper, right? So there you have infinite space to work. So scientific research is a collective process. So the beautiful idea of scientific research is that we always do it. It's not an individual activity, it's a collective process. We are in the middle of a community. For example, I came from Brazil. I'm working here for these 4 months, interacting with people from LPPI that's interacting with people of Canada, etc., South Africa. So all this community is there in this collective process. And the advances will come from what? From sharing methods, from public results, and from community scrutiny. So that is the key, for example, that I was mentioning, to try to prevent these papers that are not nice, right? So it's the community scrutiny, it's the peer review process. Sometimes, for example, if you have a paper, I have one suggestion for you to kind of separate the wheat from the chaff. If you have a paper that shows results that are very impressive, right? Try to find the papers and read some papers that are citing that paper. Because maybe someone has already given the work to reproduce the results, and they found that it's not good. Or the other way around, they were able to reproduce it, so the paper is really good, right? So when you find a paper which is astonishing, go in Google Scholar, put the name, and find the papers that are citing this paper. It's good citations. It's good. They are telling good things about the paper. They reproduce the results. This is good. There is a community. That's the astrophysics. They have something that I think is very interesting. Before publishing their paper, they put the paper in an archive, and in this archive, people can make comments. This is really nice. So they can give comments. They say, "Oh, nice paper," or "No, your paper there's something here that's not really clear. Can you clarify?" And the author works with the comments for some time. And after, when the comments are all answered, etc., everything's fine, they go and publish the paper. This is something, unfortunately, that is not really widespread in the journals. I know there are some journals where you can put comments on the papers, but this could be a good idea. But of course, the way traditionally this would be made is in the review, in the references, right? In the citations. When someone publishes a paper, others will cite the paper. Depending on what they talk about, it can be good or bad. Science progress to the collective verification, not to an individual authority. So this is something that we will see in this scandal that I will tell at the end of the class today, that most of the story built up because there was a guy, the head of the group. He was really considered in the community. So he was, I heard, I'm not sure if it's true, he was appointed to be a Nobel Prize. So he was not anyone. He was a very important person. So everything was going up. Where it comes? Oh, it comes from the Bell Laboratories. Bell Laboratories. The laboratory who invented the transistor. How come we not trust what is the science that's made in the laboratory, right? And the PI, the guy that was the boss, he was really known in the community. So sometimes this argument of individual authority sometimes surpasses some of the scrutiny that they may be a problem. So the peer review mechanism is a community-based quality control. So when you submit your paper will be analyzed by people. In principle, these people, they are specialists in the field. They will write a review of your paper without, in principle, interests, right? Not to help you or to put you down. And it evaluates the methodology, consistency, clarity, and transparency. It's true that no one can redo the paper on the file. It's very difficult. So peer review will not guarantee that everything's correct. There's no way. No way someone can review a paper except the mathematicians, right? But they take 2 years to they take 2 years to review a paper. So sometimes they redo everything. So at the end, a peer review process in math, maybe they can detect errors, they can improve clarity, etc. But in experimental sciences, it's difficult to redo everything just to write a peer review, right? but they can spot if something is not really fitting well and suggest, for example, try this, try that to make sure everything's right. That's what we see. So the scientific research and uncertainty, the idea is the scientific knowledge is always incomplete. So here's where we are sure we will have job for the rest of our lives, because there's no way we will master everything. There's always work, always something to improve, always something new. So being a researcher, you are sure you have work until the end of your life. Research is not about repeating what is known. It addresses open questions, settled facts. Uncertainty defines the research frontier. Sometimes it's important to mention that we have to repeat sometimes measurements that have been done in the past, but we are not generating scientific knowledge, right? We are just repeating. We are training, right? So if the answer is already known, it's not research, it's instruction. We are instructing ourselves. This is part of the process, right? So sometimes you go to the lab, you make measurements that people have already done, you check, you test, you are instructing yourself. Then when you are, okay, I know what I'm doing, I master my equipment, everything's fine, then you start to generate new data, new knowledge, right? But scientific knowledge, the idea, the word that we can say is inedit, is new, right? It's difficult to publish a paper, for example, on a subject that has already been discussed or is already in the past, right? We always try to push the frontier, forward and forward. So in the virtuous cycle of scientific research is uncertainty motivates questions, questions define methods, methods generate new evidence, and you start to roll the wheel, right? So research does not completely remove uncertainty, it aims to reduce, characterize, and organize. So usually when we are dealing with experiments, with devices, the amount of mechanisms there is just gigantesque, right? What we try to do is to understand what are the main mechanisms, the most important, so we can understand what's going on and we can try to make predictions. But we can never master everything, all the details, right? For example, in my case, in theoretical chemistry, there's only one molecule that we can make an exact calculation, which is the hydrogen atom. If we take two hydrogen atoms, you try to make the hydrogen molecule, it's already too much for us to give an exact solution, right? So we always have to deal on approximations, on assumptions, etc. And what we try to do to make our model the most complex as possible so we can make predictions. Because sometimes we can make a model that's so simple, it will not be able to do any prediction. Then we have to keep adding ingredients to be able to make predictions. Okay, now it comes the last topic, the ethics and responsibility in scientific research. So this is an important topic that we'll touch also, we'll close at the end when we talk about AI. How can we really do research in a responsible and ethical way? So the point in the scientific research is that trust in science relies on honesty, transparency, and accountability. So in certain sense, we still have some respect of the population, of the politicians, etc., because they trust science in the sense that scientists, they are usually, no, they will not open the, the hand of honesty and transparency for anything. The idea is not, for example, to hide facts. They just want to show the real facts, right? I have a friend, for example, he's very, very worried about electromagnetic waves. He's always asking, no, in my building they put a 5G antenna. Would that create cancer? Oh, Demetrio, have you seen there is a report saying that people that live close to antenna, they have cancer? He said, well, we are surrounded by these antennas. So the fact that you live closer to one or you try to go away from it, in principle, when you take your phone and you put close to your ear, the radiation there is much stronger than if you are 1 kilometer or 100 meters of an antenna. And I always try to put him down, but he's always worried about the wave frequency and Wi-Fi, etc. Why we are not worried about? Because, you know, there are scientists making these measurements. They are taking these cell phones, they are taking mice, putting together, trying to fry the mice to see what is the effect, if you generate cancer, etc. So in this case, we have to trust them. Scientists, they have to be honest. When scientists not honest, oh, it can generate a lot of damage, right? So in this, we have to incorporate that into our work. Transparency, honesty, and accountability, meaning if something goes wrong, make mistakes is human. Okay, what should I do? I made a mistake. I'm sorry. I was not thinking correctly. What should I do? So that's the idea. Correct the mistake. So ethical responsibility is inseparable from scientific method itself. So ethics and responsibility, we cannot separate. It has to be built in because it's part of the core value of our work. So what is the difference between mistakes and misconduct? That's what we will see in the end of the presentation. So mistakes is part of science. Hiding them is the problem, right? So make mistakes is part of science, is part of life. We can have problems, but the problem is hiding them. So honest errors, for example, flawed assumptions, incorrect data analysis. Sometimes we may write a program that has some typo mistakes, some incorrect equation. This happens, right? Limitations can be discovered after publication. This can happen, right? Sometimes you publish your paper, it passed through the peer review, no one observed. Someone from your group or someone from another group tried to reproduce the results. Oh, I found it. And what happens? You have to correct it. What is not good? Scientific misconduct, data fabrication or falsification, selective reporting. Remember the devices, right? 100 by 100, you hide 90% of the bad results. You just take the best ones and you say, this is the common device. No, this is misconduct, right? You are selectively reporting. Knowingly misleading interpretations. So you look at the data, you know it's not telling that, but you try to push others to agree or to believe that is a new phenomena or etc. So what happens if I make a mistake in a paper? It's common. I have a paper, for example, is the most cited paper I have. And we made a mistake in one equation. What we did, we had to make an erratum, which is to publish a paper, not a paper, but one page saying, look, the equation there is not this, is that. And interestingly, sometimes people cite the erratum, not the paper. So I have already the erratum making part of my H index because they cite the wrong paper. It's there. So ethical scientific behaviors requires action, not silence. What you should do, acknowledge the mistake as soon as identified, communicate with the co-authors. So we will talk in the section of the paper writing, what are the author's responsibilities, right? So once your name is on a paper, you are responsible for what is written there. There are so many cases of misconduct that sometimes complicated the life of someone that really didn't know what was going on. That some reviews, some journals, now they ask you to specify what was your role, the role of each one on the paper. And this sometimes helps people to feel more comfortable because they say, if someone happens in the experimental part, I cannot tell there was some problem there, right? I'm doing the theory. So in these journals, you say that person did the experiment, that person did the theory, etc. So if something happens, you know who to blame, right? But this is not for all journals. So in general, if your name is on the paper, you are responsible. So if something happens, communicate with the co-authors and with the editor. You can publish corrections, errata, which is, as I mentioned, or in the worst case scenario, depending on the quantity of the error or the gravity of the error, a retraction, meaning you take out the paper from the internet. Okay, so we go now to the bonus scandal. I tried to put a very horrifying picture here because this was really horrifying. It's horrifying, Karin. I think it's enough horrifying, no? So, one professor in the community mentioned that this scandal, he had this sentence: when the breakthrough physics turned into the biggest fraud in 50 years. So this happened in 1998, year 2000. And this was a young German physicist called Hendrik Schön, and he was a rising star at Bell Labs, which is one of the most prestigious laboratories in physics in the world, the laboratory who made the transistor. And he went from a rising star to a to the center of a major scientific scandal involving the fabrication and reuse of experimental data in high impact publications. The episode that was described with the most, one of the biggest fraud in physics in the past 50 years at that time is 75 years. So what happened? What was the claim? So between 1998 and 2001, this guy, Henry Schön, he was a postdoc in a Bell Labs. He was in the group of a professor called Bertrand Batlog. Bertrand Batlog was a physicist with a long story in the field of magnetism, not in organic semiconductors, but he started in this field of magnetism, of organic semiconductors. He had his postdoc, Henry Schön, and he produced a series of groundbreaking papers claiming molecular scale transistors, superconductivity in organic materials, field-induced superconductivity, and revolutionary advances in nanoelectronics. His results, they promised a new era of ultra miniaturized electronics. So the idea was using a molecule as a transistor, and a major technological science and breakthrough. The scandal was so complicated that Japan, after the scandal, processed Bell Labs because they put a lot of money in the field of organic electronics because of the works being published by Sean. And imagine a country was moved, the financing science of a country was moved because a postdoc was making fraud papers. And it was not little money, it was big money. So they opened calls to finance organic electronics because they saw what was going on. And they said, look, this field is important. Let's invest money on it. And at the end, it was all fraud. What happened? So, Sean in the period of 1998 to 2001, he published 90 papers in top journals, including Nature, Science, Physical Review Letters. 90 papers. What was I remember this time I was in the States in 2001, and my boss was very known in the field. He invited not Sean, but the Bertrand Backlog, which was head of group. And I remember as if it was today, he came to the university. It was the first time I saw a green laser, because at that time it was not popular. Everybody had that ugly red laser. And then the Backlog came in this big auditorium, and then when he pointed his laser, I said, wow, look at that, it's green. I never saw that green before. And it was beautiful. It was, at that time I remember like a red laser would cost $5. A green laser, a green pointer would cost $100. It was fancy. Huh? Bertrand Backlog showing all these papers. Science, Physical Review, Nature, Physical Review, etc. What was the most important problem that the community couldn't see, couldn't stop? It took from 1998 to 2002 to close the chapter, nearly 4 years. What was going on? Lack of transparency. So in all the papers, they only showed graphs. Methodology was incomplete. Critical experimental details were missing. And one key part, device fabrication steps, were vaguely described. So this was really clear, a clear point, because most of the papers, they were used, the devices were made with gas, with vacuum deposited crystals. And Sean said that he designed a new way to purify the organics, to create those ultra pure crystals that no one in the planet could do except him. And he said, well, we are seeing these results, these phenomena, because we have ultra pure crystals that no one has. And of course, science tells him that he has to describe how he made these crystals. He described, but in this way, vaguely. So no one could verify it. No independent verification. No independent verification. But how it took 4 years for someone to say, there's something wrong. It cannot be independently verified for 1 month, 2 months, 6 months, but 1 year, no one can reproduce the results. Is something going wrong? What do you think is the cause of that? That people keep believing in the guy, time passing, no one could reproduce such fantastic results, and only one guy was publishing and no one would say no, something changed. I believe. Is the argument of authority. I said, oh, I am, blah, 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 from Bell Labs. You believe, you have to believe me, right? So it was easy. If it was someone from Brazil, it wouldn't take one nature or one science. It will be an end of the career. But it took 90 papers retracted. It was really complicated. So, hmm? Okay. Okay, I guess. So, how he was called, that was beautiful. How he was called, how really someone started to see that, there is something really ugly behind this story. So the story says that there was a postdoc. She was having her prenatal consultation. She was bored. She was in the doctor's office with a pile of his papers, Sean's papers. And all of a sudden, she realized that two different papers had the same figure. But they were two different papers in two different systems, completely different. And she took one page of the paper, took the other page, looked in the light, graph was exactly the same. So that was really the problem. So she took that to her advisor, and they started a nasty goose chase, as they say in the States, right? Oops. So the outcome, several papers conducted scientific misconduct. What was the misconduct? Data fabrication and manipulation. Essentially, what was the interesting part? How can someone, a postdoc, fool a community for a period of 4 years? He knew what the community was expecting to see. So he knew more or less what was the feeling that, if I make a very pure organic material and I put some electric field or a magnetic field, I should see this effect which exists in the inorganic world, but no one could see in the organic world. So what he would say, what he would do, he would take Photoshop and make the figure appears as we believe it would happen. That was it. So figures were made with Photoshop. No experiment, Photoshop. So one problem, I don't know if this is true. This is, as I said, I was in the States at the time, and I heard stories, so I'm not sure it's true. But when the scandal came, of course, all the professors around Sean was a postdoc, so he had been boss, etc. Everybody was implicated, right? So everybody had to be analyzed with scrutiny. And I heard the story that his boss at Bell Labs, Bertrand Backlog, he was with his name on the list of a Nobel Prize. Because, of course, what was going on was really impressive with the results. But at the end, he went down to the table. He spent several years without not publishing much. And those people that really had a great impact in their career just because they were around Sean. But at the end, Sean, they concluded that he acted alone. But why I believe it's important to tell this story? Because this was not just a personal failure, a failure of someone, right, that tried to fool the community. This was a failure of the system, of the scientific research process, the community, the international community. And where did we fail? We failed here, in over-reliance on reputation. So sometimes this idea of the peer review that do not cover the authors and where they are, right, is a flaw. Because sometimes you look at the paper, oh, it comes from Bell Labs, from the group of blah, blah, blah. It's already 90% of the exception is taken, right? So over-reliance on reputation. Just, because of the other 900 papers the person published, this one, of course, is true, everything is fine, etc., because you already published 1,000 other papers, right? Pressure to publish rapidly. So this is also a big problem. There is such a pressure to get the results, write the paper, publish, that there is no time to really think about, to elaborate, etc., right? When this happened, for example, people said, "Oh, boss, why didn't you go in the lab to see the curves coming up?" Right? Because there was an experiment, there was a curve, superconducting inorganic materials. Okay, there is a figure that's shown, created with Photoshop. Why his boss didn't take his hand? Okay, I want to see one of these figures at the experiment as it goes. The figure being constructed, the figure coming out of the experiment. Why? And everybody says, oh, he was busy traveling, get conferences and talks and etc. No time to be in the lab with the postdoc. So that's it. Pressure to publish. Insufficient data sharing. So he was always just giving the figures, not the data. So people couldn't go and make the tests and etc. In journals, they were not demanding the raw data. So at the end, they just, okay, accept, publish, and keep going, etc. So this is a good example of that we should be careful, when publishing our papers, especially the pressure to publish rapidly. This sometimes induces error. You don't have time to do the correct analysis, etc. At the end, results will go not really polished, right? So he was caught with he using graphs. So take-home message that I want you and all of those who are listening to take home, to think about this talk today. What are the scientific questions that drive your research? So this is one point that I believe you should take off this talk. The scientific questions are the starting point. To start a scientific research without knowing well the scientific questions, and you miss some really important good start. Once you have the data, once you have the scientific questions, what kind of data will feed your model, right? So you may have to do some experiments, design the experiments, think about, are you using the temperature effect? Are you using the pressure effect, etc.? So what would be the variables of the model you will use? Once data becomes evidence, once you collect the data, you process, can your model make predictions? This is one important part of the feedback that will close the virtuous cycle, right? And most important, to avoid any kind of problems, as I just mentioned, can you design new experiments to verify or falsify these predictions? So what that means? Sometimes, for example, you have a model. I had this example once in my life, which was really productive. We had a model, we had some simulations, was just a program that we do simulations. And we had this professor, he was always asking us to try to do that, try to look at this point, try to look at that point. And the student, he was really anxious because he was already putting more than 1 year in that project. He thought everything was correct, everything was good. But this professor was always asking to, oh, do this test, do this extra test. And I was his supervisor, and I said, look, the guy who's asking to do the test, he's really good. So try just one more time to give him the answer to his question. Because if he is asking these questions, not just to be nasty, to be make you work extra, is because he's bugged with something. So just try. And he tried, and indeed, there was a bug in his software. Somewhere he wrote the wrong equation, etc., and something was not good. So this is what sometimes this pressure of publishing fast, etc., sometimes is really not useful, right? Because we end up publishing papers without good verification. And sometimes the idea is, while you are designing the experiment, always try to design also another possible experiment that may help you to find something is going on, something maybe is behind the results, and you try to find this error before it's published and it's done. Right? Oops. Well, they have references, and that's all for today.